HyperConnections. There are three papers. The first one is called HyperConnection, which is published by ByteDance, I think about half a year ago. And then there's MHC, Manifold Constraint Hyperconnections, published by DeepSeek, I think maybe a month or also a month ago. And then this MHC Lite is a improvement on MHC. So a brief introduction about the hyperconnection is that it's the expansion on the residual stream. So it's instead of having only one residual stream, it expanded to n residual streams. In the papers, they mostly use four residual streams, and they claim that it improved the performance of the network. And for the MHC, manifold constraint hyperconnection paper, it says that the hyperconnection training is not that stable because if they multiply the residual stream by a matrix, and that matrix can shrink or expand the the values, so it will become extreme values, small to zero, or it's very big values. So the MHC paper is trying to constrain the matrix to be doubly stochastic matrix, uh, whose row sum and the column sum are both one, and we can look at details later. So by using that doubly stochastic matrix, they make the training more stable. Uh,
Two things real quick, Terry. One, you got your Zoom bar on the screen. Do you know how to remove that? And then secondarily, I don't know if you were trying to show us the papers at the moment, but we could not see them. We are just seeing your Zoom bar.
I'm not showing the paper.
Okay, for sure.
Let me try. Okay, I
Yeah, there you
can
go.
move that to another screen. Okay.
Beautiful.
So then for the MHC Lite paper, is trying to improve again on the MHC one by saying that we don't need to like do the iterative algorithm to get the doubly stochastic matrix. Instead, we can use some other way uh, that is more efficient when n is small, like when n is 4. So, okay, let's go into the papers. So, first they talk about the residual connections, and something about the seesaw effect, which means let me see, sorry, I have to before. Okay, yeah. So they have in this introduction about the residual stream and the pre-norm and post-norm. They said the pre-norm is before each residual block, and the problem with that is, it addresses the gradient vanishing problem of the residual stream, but then it introduced the issue of collapse in deep representation. And there's another alternative, is the post norm. Post norm, it alleviates the representation collapse, but it also introduce the vanishing gradients again. So if if someone don't remember what that is, this is a picture from that previous big area architecture comparison. So this is yeah, in the post norm. This is the post norm. This is the pre norm. So in in the what do you say that? Okay, for like in the prenom, why it alleviates the or what do you call that? Sorry. Vanishing gradient is that it allows the gradient to flow in this residual stream from the deeper layer to earlier layers.
Mhm.
So that's why it makes the mm, sorry, makes the vanishing gradients better. And yeah, but the problem is it when you stack more layers, the deep layers, the values of the deep layers, they become more similar to each other. So it decrease the value of more layers. And the post norm is the opposite.
Do you, Terry, do you have a any insight as to, I understand the vanishing gradient issue, but I'm not familiar with this idea that deeper layers kind of lose, what they say, lose influence or something like that. How that happens?
Uh, well, I looked at some formula, but I cannot remember exactly.
Okay.
Um,
Ted, do you have any insight into
mm,
that? The second issue?
um,
I I don't actually. I do know that LLMs are relatively shallow, right? If you think about it, like a ResNet 151 is
Yeah.
not that special of a CNN, and we're talking 150, and here today we're talking about small LLMs in the 3 billion are around 30 layers, and then giant ones are around 60. So there has to be a reason why people aren't going deeper than that. Um, because it's very clear that other models we build are deeper. But I wasn't familiar with this particular phenomenon being the reason why they don't go deeper.
Okay.
yeah, identity collapse pronounce easy to shrink. Roughly fixed scale, the model can reduce the actual change
Oh, is that,
simply by shrinking. Yeah, I'm asking
yeah,
this question too.
yeah, that there's a little bit of that first sentence or first paragraph of the collapse of representation tends to happen
Yeah.
because the architecture makes do nothing
Um,
easy. So rather than fix it all at one layer, they'll just do a little bit of fixing it at all the layers.
yeah. Yeah, actually, I read this before, but I actually don't fully understand
Yeah, yeah, why?
the mechanism behind. Um,
Okay, sorry, I
okay.
didn't mean to derail.
Yeah, no
It was
problem,
just
no problem.
something I
Yeah.
hadn't heard before.
Um, yeah, so yeah, here's a sorry. Here's a graph. Yeah, we can skip this for now. We will have another good looking graph later about the hyperconnections. Okay, so yeah, given the pros and cons of pre-norm and the post-norm, they ask this question: Can neural network learn the optimal strength of connections? And they in this paper said yes, you can kind of have the mix of pre-norm and pre-norm, the pre-mix of pre-norm and the post-norm by using hyperconnections. And the pre-norm and post-norm can be actually expressed by the hyperconnections with some special parameters. Yeah, it's learnable depth connection, and okay. Yeah, this picture is actually yeah, they divide the connection pattern into depth connection and width connection. Um, you can think of it as yeah, the depth connection. I think it means you just adjust the connection pattern between the what is that? Between the layers, to say between the attention layer and the feed forward layer. No, sorry. You adjust the connection pattern between the residual stream and the layers. That's depth connections. And the width connections is that there you adjust the connection pattern between the multiple the residual connections. So here you have waves that controls the flow from the two residual stream to each other.
And those are
Uh,
learnable parameters, are they?
yes, they are learnable parameters. And yeah, all these green, blue, yellow dots, they are all learnable parameters.
And are they those scalars? They're
These
not transformations, are they? Just scalar?
Yes, I think so. Yes. They're
Learnable scalars,
actually
yeah.
learnable scalars. Yeah, but they use matrix to hold these scalars. The
Yeah,
matrix
this
or vectors.
yeah, this figure two is showing just if you had two residual streams, not the general case of n,
Oh,
which could be four. And so for simplicity, with just two, it's easier to show scalars.
Yeah. Okay.
but the point is that the H vectors are not transformed, they're just scaled and summed.
Yes. They
Yeah,
are not
okay,
transformed. They are just scaled.
gotcha.
Okay, those post-trend unexpected, learnable. Different, yeah, they just talk about this different connections with connections. Okay, dynamic. Um, okay, yeah, this dynamic hyperconnection, there they distinguish between the static hyperconnection and dynamic hyperconnections, which means the static dynamic connection means those parameters are trained, those scalars are trained, and they are fixed in the inference time. The dynamic one means they train something and they use the inputs or the hidden state to determine these parameters.
At inference time.
Yes, at inference time.
Okay.
So they train something else,
Yeah.
and then they use that to determine these scalars. Okay, yeah, they claim that the the dynamic HC converges 1.8 times faster, and yeah, show improvements on this ARC challenge. Is this paper? Yeah, this is showing, why it's not jumping to. So yeah, if we look at these diagrams, it's showing that to reach a certain loss, it's 1.8 times faster.
And is it reasonable to assume, oh, maybe it says right here that I'm wondering about the so the model here is I have my residual stream split into multiple pieces, maybe four pieces. Is the total width of if I sum up those four pieces, is that the same as the baseline? If that makes sense. In other words, it's not four times as many residual streams. It's just the same size residual stream split into four pieces.
It's split into four pieces, but when they feed into the layer, the attention layer, they merge those pieces together. Uh, yeah, maybe we will go through the details later, I think.
Okay, okay, sorry.
Yeah, and no problem, no problem. Yeah, it's just later I will show a picture. It will be easier to explain on that picture. What is that? Okay, method connections. Okay, I think it's time to see the picture. Yeah, this picture is actually screenshotted from the video that good video Ted shared. So these X, one, two, three, four, they are residual streams. So instead of just having one residual streams, you have four of them. And then let's look at the purple lines. They are merged into this XL pre before feeding into the layer F, which is the attention layer and the feed forward layer. So you see this alpha, these alphas are learnable parameters. It's just a weighted sum of these four residual strings. And then after X forward, yeah, okay, this XL pre, I think, oh, yeah, these, okay. So for the out, I think this is the output F, this whole thing, FWX pre, this is output of the layer. And they multiply by this beta to produce 4Z vectors. I think this guy beta is just a column vector, and then this FW is yeah, it's the output of the layer, so it's a row vector. We multiply them, it's just producing a matrix out. So they are you can think of them as expand the layer output into four residual streams, and each of them is merged into mm, the incoming residual stream, which is X, those four X. And there's another change, another thing is these H. Um, so what they do is they mix the residual streams into each other, or you can think of as exchange the informations between those residual streams. So so that's how they like make the residual streams n times, but still the dimension of the layer dimension is still remains the same. Um, any questions on this?
Yeah, so my question, I guess, would get back to when you're comparing this to the baseline. So you've got four residual streams, each of width. Oh no, this is layer, not that doesn't say what the L is the layer number, not the width.
Yeah, yes. The width is yeah, actually mm, the width
Doesn't show
of
up here, it looks like.
yeah, no, it doesn't show. The width is just the normal width. If a baseline model is 1,000 dimension, then this would be 1,000.
Okay, and then you would have, like in this case, you'd have X1, superscript 1, X superscript 2, X superscript 3, and X superscript 4. So you would have 1,000 for each one of those. So kind of almost effectively a 4,000 wide residual stream.
Yes,
And then
yes.
it's kind of, in my head, I'm thinking of it as kind of weight sharing with this layer, this FWL. You're doing weight sharing for each one of those 1,000. They all share the same set of weights.
Sharing or the same weights. Oh, you mean these layers?
Yeah, in there, right.
Yeah,
You're
yeah,
just
yeah.
using the
Yeah, they
same weight
share.
4 times.
Yeah, yeah, that's right.
Okay, okay.
Yeah,
And
and
I,
if I can jump in,
sorry.
the actual mechanism is slightly different because it's not sharing weights, it's actually projecting those 4,000 down to 1,000 before uh, doing its thing.
Oh, okay. That little purple lines are actually a projection into a 1,000 width.
Yeah. So XL pre, just like Terry was saying, will be 1,000, just like XL1 and
Okay.
2 and 3 and 4 each 1,000. Now, what's was a little surprising to me, I guess this is because of the compute involved. It's actually not even just a down projection, which would have some more cost to it. It's literally just a mix of 1, 2, 3, and 4. So you could say like zero point 0.5 times x1 plus zero point 0.3 times x2
Okay.
plus zero point 0.2 times x3 plus zero point 0.7 times x4. So it's not mixing it channel wise. It's just,
It's kind of
you
a
know,
weighted superposition
yeah,
algorithm.
exactly. That's all it is. So it's actually fairly low complexity, low compute.
How about the top end of that then, Ted, where you project out back out to four streams?
I'm not sure if I fully understand this diagram outside the context of the video, but it is the same phenomenon where basically you simply have a single 1,000 output and you get to attenuate how much it gets written to each of the four. So if you wanted it only to get written to X1, you could do 1,000. If you
Okay,
wanted it to
gotcha.
be half X1 and half X4, you could do 0.500, 0.5. And you could just decide to write to all of them. So you could do 1,1,1,1.
Yeah, gotcha. Okay,
Um,
interesting.
yeah, yeah. Okay. So we can go to next. Yeah, these are just methods. Static. Yeah, these are just the formulas about what we just talked earlier.
Mhm.
Um, Depth connections and the width connections. Yes, they separate the formula for those depth connection, width connections, and the dynamic hyper connections, HC.
Hey, Terry, can I make a
Uh,
quick comment here?
yeah.
So rather than doing this hyperconnection stuff, a very simple thing you could do is just actually increase your residual stream from 1,000 to 4,000. And so it is a viable option and it would actually work. It would actually give you a model that is stronger than the base model with 1,000. The problem with that is that the width of the residual stream is the primary driver of the number of parameters you have. So if you
Mhm.
multiply that by 4, ballpark, your number of parameters is going to go up by 16, by a factor of 16. Okay. So this paper is really about, is there a way we can get some of the benefit of a wider residual stream without paying the cost of quadratically more parameters? And and they were able to, in this first paper that Terry showed, they were able to get some of the benefit without growing the number of parameters. It's just that, as we said, it did then result in some stability problems once people tried using the technique for billion parameter, not 100 million, but billion parameter LLMs. It started to break.
Mhm.
Yeah, yeah. Yeah, so
So
yeah, sorry.
Yeah, I was going to ask Ted. So, if I think of this as kind of from a computer architecture perspective, um, I guess I've thought of the residual stream as something that could have multiple kind of quote unquote registers in the residual stream that exists because of superposition. Um, in this case, is it reasonable to think of it? They're actually now providing a physical separation between that type of state vector register slash register into separate streams, allowing you to operate on one, maybe multiple if they're superimposed, but let's say one register at a time.
Yeah, I think that's a good intuition. Um, there's some limitations because it's just doing this mixing. It's not allowing you to pick any subset of 1,000 dimensions out of the 4,000,
Yeah,
right?
yeah.
But I do think of it a little bit like a somewhat limited ability to have scratch space. So your
Right.
residual
Yep.
stream's 1,000, and you're giving it 3,000 scratch space. And at any point in time, it can choose to use scratch space one instead of the main residual stream.
Yeah.
And it can later read that, but eventually it has to write everything sort of to the main residual stream so that you can do your next token prediction. At some point, it will have to do that sort of.
Right. Right. And that kind of it might intuitively it kind of makes sense that superposition. It seems like if you make it wide enough, you can superimpose as many um, vectors as you want. But each transformation, like you said, grows as a n squared, so it becomes very expensive. So this is kind of an efficient way to make a very wide residual stream without the cost of the forward transformations.
That's right. Like you and I have talked in the past about making the residual stream variable width, maybe
Yeah,
fatter in the middle and skinnier at the beginning and the end layers.
right.
And so this is the ByteDance team saying, we can actually give you some of those benefits of wider in the middle without literally paying the price of extra parameters for those middle layers.
Yeah.
And I think that's why they kind of stop around four, because it turns out that if you give it 20x scratch space, it doesn't really need that much scratch space,
Right.
right? If you have 36 layers and the first 20 layers all write to unique scratch spaces, there's not much time to actually pull in those results and merge them back into one thing, if you think about it.
Yeah. Very cool. Thanks, Terry.
Yeah, yeah. Thank you. Thank you, Ted. Um, and the initialization, yeah, this just talk about how they initialize that. Why super connection, hyperconnections, residual connection, and non-trainable. Yeah, here they just try to express the prenorm and the postnorm as their hyperconnection matrix. Uh, yeah, the prenorm is easier to understand. It's just a simple one. The postnorm is they have something in the appendix to describe how they derive this. And also note that this for postnorm, the weights also depends on the variance and the covariance of the input output. So postnorm is not that matrix is not trainable. Um, okay. Yeah, here they discuss the sequential parallel duality. I think what they are trying to say is that they can mimic a sequential arrangement of layers and the parallel arrangement of layers by having this type of two residual stream and two-layer network and varying the connection parameters. Um, okay, the results compression. Oh, I think this just yeah, they run the experiments on different number of residual stream, ranging from 1 to 8. I think this just shows that the 4 and 8 they seems better than others, but noticeably that the one residual stream alternative is worse than the baseline. So they said in this paper that that you need the n number of streams to be greater than one to make a performance increase. Um, so that actually I'm yeah, so that actually makes me think that what is actually the width of the residual stream that makes performance better instead of the mix the connection patterns. Um, yeah, they also tested the variant about with and without 10H activation function. Um, yeah, seems that the 8 residual stream one is somewhat better than the 4 residual stream one. But yeah, but I'm not sure why later on the MHC paper they all use the 4 residual stream one. Maybe it's a little less computationally expensive.
Hmm.
Yeah, I think the 4 and the 8 are pretty close. So you're not seeing much benefit from this further doubling of things,
Hmm.
right? You can see a couple of
Yeah.
the benchmarks, the 4 actually did ever so slightly better. So maybe on average, the 8 does a little bit better. But yeah, you know,
Hmm.
you could
Yeah.
see
Yeah.
that maybe, 6 would be a little better, but it's not. It's
Hmm.
not clear you get much benefit past 4. And again, I don't know that this is a perfect analogy, but if you think about it as scratch paper, you know, if you're taking a
Hmm.
math test and you have to do all the calculations in your head, you're not allowed to write anything down. You might not do so well. And if I say you have scratch paper and pencil and you can write things down, and you might do better. But at some point, if I give you 100, 1,000, a million pieces of paper, it's not going to help you. You just needed a handful
Hmm.
in order to be able to write some things down.
Hmm. Yeah. 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 Right. Okay. Ablation study. Yeah, they also studied the performance of the static one and the dynamic one, and with and without 10H. So it seems without 10H slightly better, and the dynamic one and the four. Uh, I think they also did some B models. Where is that? MOE
Hey Terry,
models.
what's
Yeah.
the V2, V3 at the column headers?
Oh, sorry. Which one?
Just the table, the column headers, V2 eval, V2 eval PPL. What's the difference between V2
Um,
and V3?
I I'm not sure. I
Hmm.
think they are just different benchmarks. Actually, I
Okay.
didn't look into these things.
Okay. No, that's fine.
B2 eval 10H. I think they did something saying that okay, I forgot where that is. Yeah, but this one visualization analysis, this is something interesting. So they draw this picture by calculating the connection strength. What is that called? Connection strength? Hyperconnection with and the transformer layer. What is that? Uh, okay, I can't find that word, but this graph shows that how much impact uh, a layer gets from its previous layers. So for prenorm, the the later layers, for example, 28, it gets impacted by all previous layers. And for post norm, the later layers only is impacted by a few a few previous layer just
Hmm.
adjacent to it. And when they look at the hyperconnection, uh, it's a mix of the both. So for example, the shadow the first and the zero layer and the two layers, they have impact almost all the later layers, and there's also the it's mostly most layers have uh, has this kind of decayed impact from previous layers. Um, yeah, so it's another proof of it's a mix of prenorm and postnorm.
Hmm.
Visual inputs are yes, related work. That's okay. I think that's it from the first paper. Um,
Carrie, a couple questions on that. The visual that you just had there with the influence of one layer to do you know, is this for the static connection weights
oh,
or
good question. I didn't pay attention to that.
okay.
I think it's dynamic.
So it's averaged over some data set?
Yeah, yeah.
Okay. And did I miss, did we show where the dynamic um when you have the dynamic hyperconnections weights, where was that computed?
Oh,
You might have showed it earlier. Maybe there's a formula. I didn't
no,
really see
no.
it in the.
I didn't show. Sorry. Let me bring that. Uh, initialization,
Oh,
dynamic
it's right
one,
there. So there's
hyperconnection.
okay.
This guy.
So those are the equations. It wasn't
Yes.
shown. It's not shown like in a block diagram, but that's the equation.
Yeah, yeah. So
Okay.
it's just the the stream multiplied by another matrix. This is parameterized,
Yeah.
trainable, and then go through a 10H activation, and then again another trainable
Yeah.
scalar. Yeah,
Yeah. Yeah. Okay.
and yeah, also they plus another static static trainable parameter. So it's a mix of static and dynamic.
Gotcha.
Mm. Okay, so we can go to the second paper, which is from the DeepSeek. So yeah, these just by expanding, yeah, they just talk about hyperconnection, restore. Yeah, they said that the problem with the hyperconnection is it compromised the identity mapping property for the residual connection. So you don't have the direct connection from deep layer to shadow layers. So your gradient can be large or can shrink to very small values. Uh, okay, these are all the introductions that has been covered in the hyperconnection paper. Okay, this is the same formula as in hyperconnection paper, and they expand it by multiplying the matrix out. So the intuition is that this H res matrix can be not that well can be not that good, so that when you multiply them together, the value can be large or small. Related work. Yeah, they also talk a bit about micro design versus macro design. I think for micro design, they're talking about the improvements inside those blocks, like inside the attention layer or feed forward layers. For the macro design, I think they mean the connection pattern between the layers. Yeah, I'm still not so sure why they brought this up. But yeah, this is, I think they are saying that this hyperconnection and MHC is a macro design improvement.
Yeah, that's
Preliminary,
right.
yeah.
If I could add a comment, by count, there have probably been thousands and thousands of papers that talk about how to change the attention layer in the micro design. And maybe not
Mhm.
quite as many, but still, there are a lot of papers that talk about how to change the feed forward layers. So famously, the original attention is all you need. MLP had two sets of weights, and then Llama introduced this gated MLP that has three sets of weights. Um, and then, of course, mixture of experts is uh, more recent. So we've seen a fair amount of iteration and improvement on those. But how you connect all these layers has seen many fewer papers. I won't say there's been none, but just many fewer. And so I think the ByteDance authors wanted to point out that there's an opportunity for researchers for more papers on this topic of how we connect things. Um, and part of the pressure is that for a while, people just said, build the model bigger and bigger, more parameters, right? GPT-2, GPT-3, GPT-4. But then we started to run into issues with we don't have enough compute to go up an order of magnitude on that. And then people realized, oh, train it on more data. And so, you go to hundreds of billions of tokens, you go to trillions of tokens. Unfortunately, we're now running out that area too, where we've scraped the entire internet. There just isn't, the ability to go up a factor of 10 to 100 trillion tokens. Uh, so maybe one of the things we should do is we should try and improve our macro design and optimize the way we're using the residual stream. There is actually a fourth bucket, which um, they don't mention here in section 2, but I think we also are starting to see because of this pressure where we're running out of compute, running out of data, more papers talking about tokenization. So, the large concept model, the byte latent transformer, different ways of doing tokenization, those are another direction for saying, well, maybe we keep the model the same, but we improve the tokens that we're putting into it. And again, I think a lot of this is the pressure that we can't just keep going bigger on parameters and data. So we have to get better on other stuff.
Mm. Yeah, question about tokenization. Is that the same tokenization that convert the words sentence into tokens, or is it something else?
Yeah. So some form of byte pair encoding sentence piece, is what we use, I
Oh,
think,
okay.
in all commercial LLMs. But there's a lot of people now saying that this theoretically seems quite suboptimal. Nobody's figured out what to replace it with yet, but at least
Hmm.
theoretically, it feels very suboptimal.
Oh,
Mhm.
oh, okay. Okay. Thank you. Um, yeah, preliminary. Yeah, this is just a hyperconnection formula. Numerical instability.
So Terry, if you could pause on that table right there, the ablation table
Oh,
one. Yeah.
this one? Okay.
So this is an important table, I think,
Oh,
uh, because in the hyperconnections paper, I had a little trouble understanding their terminology, and I actually like the way this paper organized it. They said there's
mm,
basically three things going on. You've got multiple residual streams, and before your layer, you're going to decide how you're going to grab a subset. So let's just say it's 4,000. How we're going to grab 1,000 out of that 4,000. And that's the H pre matrix. That's the decision how you grab it. Okay. And then when you're done with your computation in the layer, whether it's attention, MOP, whatever, then you have to decide how you're going to write it. You only have 1,000. You have to decide how you're going to write it to 4,000. So that's the H post. The other thing,
mm,
which was not obvious to me, should be part of this hyperconnection design, but the way they built it, they just did everybody talks to everybody. And so there's this thing, the HRES actually happens in parallel with the layer. So you have an attention layer, and things are going in and things are going out of the attention layer. But in addition to that, what's happening is the four residual streams can mix with each other. Okay. And what this ablation says is, well, if we actually turn them on and off, where do we get the benefit? And so if you're thinking about scratch space and whatnot, maybe the greatest benefit would be having like H pre um, and
mm.
being able to pull from different parts of it. But it turns out that by far the largest impact comes from this residual stream mixing that's happening in HRES. Okay.
Yeah.
So the ByteDance team tried training a hyperconnection model that was bigger than the original hyperconnection team. And they ran into some problems. And they saw that they're having problems with like vanishing and exploding gradients. So a simple solution would be get rid of HRES, only keep the H pre and the H post. But it turns out that the benefit comes from that HRES. So they did not have the option to just get rid of that part. So what that meant was they had to find a way to fix HRES and make it work better. And so that
Mm,
ultimately is the entire motivation for this paper to say we're going to improve HC. Ultimately, they called their improvement MHC because they couldn't just get rid of it. They had to actually keep it. So they found a way to make it better.
mm,
Ted, I'm struggling a little bit with so I can see where they tested with HRES and not HPre and HPost. But I don't see a ablation of HRES. In other words, if you had HPre and HPost but no HRES, what do you get?
Yeah, I I hate the way people do ablations. Um,
It should be a matrix, right? Not
well,
not a single table like this.
in a perfect world, you could do all two to the n
Yeah,
combinations,
right,
right?
right.
So you're saying a matrix, there would be eight different combinations.
Yeah.
Um, uh, I do think that if you are limited in your time and resources and the amount of space you have to uh, uh, fill up the paper, okay, if you were only going to show three, I would want to say do it without HRES, but keep the rest, without HPre, but keep the rest, without HPost, but keep the rest, right?
Yeah. Yeah.
Something
Mm.
like that, so that they're all being compared to the same baseline,
Right. Right.
Yeah.
right? But I see in so many papers, the ablation they do is without thing one, without one and two, without one, two, and three, without one, two, three, and
Right.
four. And it's not clear what would have happened if you just took out thing four because
Right.
you've contaminated things.
Yeah.
So
Yeah.
so you either start with nothing and add just one thing, or you start with everything and just remove one thing. To me,
One thing
those
at
are
a
the
time.
most important experiments.
Yes,
Uh,
I would
but
agree with
this
that.
is not the only paper. I would say the more than half, the majority of papers that have an ablation, it's something like this where they don't do things in parallel, they do things sequential.
Hmm.
In this case, the gap is so big, right? 0.22 versus 0.003, right? Like
Mm.
it's 7 times bigger, 7, 10 times bigger than the other two. So probably if you did the other experiment that you're asking for, it's probably the case that HRES wins. But I completely agree with you that this is, in my book, not the right way to do an ablation.
Hmm. If they're pulling H pre and H post out, what does that mean? Does that mean they just use, oh, maybe it says it right up there, uniform weights of ones for H post. Yeah. Yeah. Hmm.
They did they say what they use for each res?
Well, I was reading that line right above it and assuming that
Yeah,
that meant
yeah.
if you've ablated something,
Oh,
then you
yeah,
essentially just
identity.
use
Sorry, yeah,
identity
yeah, yeah, yeah.
matrix. Yeah.
Ah, yeah, yeah, yeah.
Yeah.
That's the
Yeah.
identity. Yeah.
So basically no mixing. Yeah.
Mm. Yeah, yeah, that's correct. Instability. Yeah, they then investigate the numerical instability of HC. First based on value. Yeah, I think they just show it from the graphs. So they use the MHC as the base, and yeah, they draw the HC what is that? Absolute loss gap. Yeah, it's
Mhm.
just showing that HC is not stable here. And gradient norm also is the HC. This one is not so obvious. HC gradient norm. Yeah, this one is not obvious. And the single layer mapping is HC forward, HC backward. Yeah, this is they calculate the HRES. This is for single layer, HRES for single layer, and this is HRES multiplied across layers. They are saying that this Amax gain, I think, is just the norm of the matrix.
Mhm.
It can go to extreme values instead of just close to one. So that's I think they're saying that the constraint is necessary. System overhead, memory cost. Okay, they also talk about the memory access overhead. I think they have some calculations done in this table. read, write, they calculate the, yeah, each the how many memory access do you need? So when n is 4, yeah, I'm not actually sure the implications, but yeah, it's probably very costly. Okay, methods, manifold. Okay, so yeah, they want to enforce the href, the yeah the what they want the gradient flow to not explode or to not diminish uh, by making the matrix href matrix to be doubly stochastic. Where is that? Oh yeah, the doubly stochastic. So the doubly stochastic matrix means row sum and the column sum are both both equal to one. The why it's called doubly stochastic because there's a concept of stochastic matrix where only a row sum or only the column sum is one. So there's a distinction between the left stochastic and the right stochastic depends on where you put the matrix, where you put the matrix. So the good thing about this doubly stochastic matrix is when it's multiplied when it multiply with another vector, it preserves the norm. And it's also compositional closure. So that means you multiply multiple matrix, it still remains doubly stochastic.
Hmm.
Uh,
Hey
and
Terry, can
then
I add a
yeah,
little color here?
yeah.
So going back to the singly stochastic matrices, where
Mm,
you see these a lot is things like Markov processes, or if you're doing graph traversal, okay,
mm,
um, then basically if you start in a certain node or state and you have a transition rule that says you're going to one time step later, you're going to be in some other state. Now, the state could be yourself, the same state. The state could be a different one. But like the probabilities have to add up to 100%. Okay. If you are in state 5 at time step X, then at time step X plus 1, all the possibilities of what state you're in, they have to add up to 100%. Um, and again, that can include state 5 staying in your state, that can include all the others, but they have to. And so that's why these transition matrices, again, depending on whether you left or right multiply, you see that the columns or the rows always add up to 1. Okay. And
mm,
so you can think of this as sort of like mass preserving. In this case, it's probability mass preserving. Um, And so if you only have a 25% chance of being in state 5, and then you have this transition matrix that says what are the probabilities you wind up in other states, when you multiply that out and you sum those up, those are all going to sum up to 25%.
mm.
Okay.
Yeah.
So now if we use that here for HRES, then you can set it up so that in the forward pass, you if you started with if you have four residual streams and they all have sort of similar magnitude, similar size, um, then if you use a stochastic matrix that they add up to 1, then you can say like, oh, give me, half residual stream A, a quarter B, a quarter C, and 0D, and then you're going to wind up around the same size, assuming they all started out the same size, right? or you could
Mm.
do a third, a third, a third zero, or you could do 4/4, or you could do whatever. But as long as they add up to one, you're going to wind up with something the same size. So I don't know if this is technically the right way of thinking of it, but I think of it as sort of L1 norm uh, maintained. Okay. The problem with a stochastic matrix is that then when you do back propagation and you go through multiple layers, it doesn't have this property. It only has this property in the forward direction. Okay.
Mm.
Because the way you sum gradients, right, you're summing from the outputs of a given layer, not from the inputs of a given layer. This is why if you then have a doubly stochastic matrix that not only the rows but also the columns sum to one, then in the reverse direction, it also looks like a stochastic matrix when you're doing the gradients.
Mm.
So now it looks like a regular stochastic matrix for the forward pass, and it looks like a regular stochastic matrix in the backward pass. And in both cases, it's sort of summing to one and sort of L1 norm preserved.
Mm. Yeah. That's very good point. Yeah,
Yeah.
that's why it has to be doubly stochastic.
Mm-hmm. Exactly. Because
Yeah,
stochastic
yeah,
would help you in one, but not in both directions.
yes. Yeah, we need the forward flow and the backward flow both to be consistent, to be like stable. Yeah.
Yeah, because otherwise you could still have vanishing and exploding gradient.
Mm. Yeah.
Yeah. And then this compositional closure just tells us that um, if you multiply by a doubly stochastic matrix, and then you multiply by a different doubly stochastic matrix, and you keep multiplying by more and more and more doubly stochastic matrices, by virtue of their special properties of everything summing up to one, um, they cannot have eigenvalues greater than one. And when you multiply matrices, square matrices together, then you sort of multiply their eigenvalues. And so if you start out less than or equal to one, then no matter how many times you multiply positive numbers that are less than or equal to one, you're going to stay less than or equal to one.
Mm.
The strength of this is you cannot have exploding values because they force the combined eigenvalues to stay less than or equal to one for true exact doubly stochastic matrices. What they don't point out, however, is that you can have vanishing values. You can't have exploding values because it can't get bigger than one, but you can actually have eigenvalues that drop very rapidly close to zero. So
Mm.
if you want eigenvalues all plus or minus one, I believe what you want is an orthogonal matrix. And orthogonal matrices preserve L2 norm instead of L1 norm. And I believe there may be some reasons why orthogonal matrices are not great because they might not do as much mixing as doubly stochastic matrices. But I think the other problem is there is no fast algorithm for calculating orthogonal matrices. Um, uh, uh, in this paper, they will show there is a relatively fast algorithm for approximating doubly stochastic, but there isn't one as fast for orthogonal matrices.
What are the sizes of the matrices that we have to calculate, either doubly stochastic or orthogonal?
They're teeny tiny. They're 4x4 matrices.
Yeah, okay, that's what I thought. Yeah.
Yeah.
And that's not doable?
No, I think 4x4 you probably could. Even if it's n cubed, you're still just talking about 4 cubes. You're talking about
Yeah.
64
Yeah.
whatever row operations in order to turn it into an orthogonal matrix.
Hmm.
But so I don't know. There may be some downstream to orthogonal, but I was thinking when I read this paper, you don't have to use doubly stochastic. You could use orthogonal.
Mhm.
Mm.
How is this
Now,
constraint? Is it going to cover later on? How is this constraint imposed on the either the model or the training?
Yes, yes, the next it'll
Okay,
get to how
okay.
you calculate this. But
I'll
right
stand
now
by.
they're just simply saying that stochastic, doubly stochastic is a desirable constraint for HRES because it has these properties. And I
Okay.
interrupted Terry before he even got to the third one.
um, yeah, thank you, Ted. And also I have a question. How does this diminish to zero?
Sorry,
As
not the product of the HRESs, but the eigenvalues can
oh, the icon.
can shrink.
Okay. 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 So in some direction, it can lose some directions.
Yeah, so imagine that you just have a two-dimensional residual stream, okay? And on
Mm.
residual stream one, I have the vector pointing north. And on residual stream two, I have the vector pointing east. If I say um, um, half north plus half east, or something like that,
Mm.
uh, I'm well, yeah.
Yeah,
So
yeah, yeah. Got it.
so if you have a new vector that's zero point 0.5 comma zero point 0.5, the length of that vector, zero point 0.5 comma zero point 0.5, is going to be um, square root of 2 over 2, I believe.
Oh.
Okay, it's going to be 1/2 of square root of 2. So it's going to be 0.707. So you've shrunk your vector by mixing two perfectly good length 1 vectors. And
Mm.
if you keep doing this, the vector can keep getting shorter and shorter and shorter because it's not preserving L2. L2 is the length of your vector. L1 is
Mm.
just summing up all the components. So you can see that zero point 0.5 plus zero point 0.5 still equals 1.
Mm.
Mhm.
But I think what matters for us more is sort of Euclidean norm, not Manhattan sum.
Mm. Yeah. Okay. Okay. Yeah. I think I got it. Okay. Thank you.
Yeah.
Thank you.
Yep. So all I'm saying is that even though this is preserving some something or other, your vectors can actually keep getting shorter and shorter, smaller and
Mm.
smaller. And if you did this infinitely many times, you could actually wind up with approximately zero, nothing left.
Okay. 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 Thank you. Um, parameterize. Okay. These efficient measurement projection.
Yeah. So
Is this
so
what the Rogers question here?
yeah. So this is where the
Parameterization and
synchord
manifold
NOP
projection.
algorithm comes in, but they don't really explain it in the paper. They're just sort of like, hey, this algorithm exists.
Oh, the algorithm. Okay, yeah, the algorithm is very simple. It's actually, I found this piece of code online. It just does the synchron NOP algorithm. What it does is it iterates through two steps. Step one is make the row sum to one, and the step two is make the column sum to one, and they just keep doing it in some steps, like for
Hmm.
example 20 iterations, then you get a very good approximation to that doubly stochastic matrix. Um, Also,
Okay.
there are some mathematical proofs about the convergence of this, but I didn't read that, but there are proofs. Um,
Yeah. So for the purpose of the MHC paper, summing up the values in rows or columns is very cheap, right? It's not too hard.
yeah,
And then
yeah.
dividing each row by its row sum, dividing each column by its column sum, that's one matrix multiply. That's pretty cheap. Um, and so in the end, their implementation in the code they share, they do this 20 times.
And is
Uh,
how and they do that, is that being done like in a forward pass? Does the gradient have to flow backwards through that entire loop?
that's um yeah, that's something I've been thinking about a little bit, and I haven't quite fully wrapped my head around. Um, if if you and I are just running Sinkhorn not for the purpose of training a neural network, just in general, you want to run
Yeah,
it, okay? And you do 20 iterations, you will have, if you keep a record of everything you did, you will have 20 column sums and you will have 20 row sums from each of your
right.
iterations. You can
Yep.
actually combine all of those together. Okay. So if the column sum from the first iteration was 5, okay, and the next one was 2, then if you just divide the columns by 10, it's the same thing as doing those two separate iterations. Okay. So for 20 iterations, if you've got 20 column sum numbers, you can just multiply all 20 of them together and just do one iteration. You don't need to do them individually.
Uh, I thought it was iterative. I mean, you do the column sum, not you have an
You you
original or
you do it iteratively, but you get the same result no matter what order you do the column and the row iterations.
oh, I see what you're saying.
So you could actually divide by column one sum, column sum two, column sum three, all the end result. If you went back to your original matrix and you divided the columns by all of those 20 column sums, and then you divided all the rows by all those, you'll get the exact same result as if you alternate them the way the algorithm actually does it in practice.
Oh,
So the operations are whatever commutative, associative. You can reorder them. You'll get the
okay.
same
That
result.
was, I'd have to think about that. That's
Okay.
not entirely
And
obvious to me,
so
but okay.
because you can actually just lump them all together, okay, I think Wikipedia maybe, one of the places that defines what is this doubly stochastic making process. Okay. It says you can have a matrix A, okay, and you can basically Sinkhorn Mop, the theorem says basically if you have a diagonal matrix C for columns and a diagonal matrix R for rows, that C times A times R will equal a doubly stochastic matrix. No, for any A that has positive only values.
Okay.
Okay. And C and R are just diagonal matrices. And diagonal matrices, they whatever. You can do a lot in terms of reordering, moving,
Right.
da, 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 you know. And so it doesn't matter if you have like 20 diagonal matrices on the right. You can just smush them all together.
Gotcha.
Okay. Um, so that's the thing. So that if you did this infinitely, then
So that makes it a more efficient calculation of it, but it's still if this is a constraint, it's either going to be expressed as a loss or it's something we do in the forward pass.
so HRES is a learnable set of parameters for your model, right? You have attention
Right.
weights, you have feed-forward weights, and you have HRES weights.
Right.
So we do need a
You need the
way
gradient
to
flowing back into that.
calculate the gradient with respect to the loss.
Right.
Yep.
Mm. Yeah. Um, okay. Maybe we can go to next. Yeah, they talk. Okay, yeah, this is. Yeah, before that, they said they implement this MHC with overhead of only 6.7, but that is based on the fact that they have to write their own kernel fusion to implement all these matrix operations. Uh, yeah, here they talked about the details of that. Um, yeah, I'm just going to skip that. I didn't really look into much details.
Yeah, I didn't
Also,
think these details were too important, but just it is good to understand that when you're training a model, not so much when you're just doing inference. When you're training a model, it has to store all of these activations. Okay.
hmm,
Because that's what's used to calculate the gradients for backpropagation. If you multiply your residual stream by 4, you're actually increasing a lot of your activations by a factor of about 4. Not all of them. Inside the layer, some of them are smaller, but you're increasing a lot of them by a factor of 4.
uh,
On top of this, if still using, if you're not using muon yet, if you're using Atom, then Atom stores momentum and squared momentum for everything, and so you you run the risk of basically this this MHC model will need more GPU memory to train than the regular model would have. So they have to do a number of tricks in order to try to keep that memory down. And one of the tricks they do is the recomputing. So
yeah.
they literally say like only every 2 or 3 layers do we actually store the activations because the activations are so big. Um,
Hmm.
and this does make it more expensive. It has to recompute the forward pass in order to get those activations back. But they've, you know, ByteDance, um, DeepSeek has shown they have some pretty darn good engineers there. And so they figured out a way to get all this overhead down to 7%, which is pretty impressive.
Hmm.
So
Yeah.
if it just worked but was slow, it would be a nice theoretical result. Because it works and they got it to be pretty fast, now it's actually a lot more interesting. It's not just a theoretical result.
Hmm. Yeah. Yeah. The optimal. Okay. Yeah, these are the details. Overlap. They also overlap the communication in dual pipe. Yeah, still, I forgot what dual pipe is about, but I think they were able to put these matrix calculation inside the dual pipe to make it not so expensive. Um,
Yeah. Yeah. The bottom line is if your residual stream's 4 times as big, then your communication between GPUs is going to be slower. So they needed to figure
oh,
out a way to increase
Hmm.
the compute chunks in order to hide the time for that communication.
hmm,
So they had to retune their whole uh, um, parallelism strategy. But but yeah, it's just a tuning thing. In the grand scheme, there's nothing theoretical that's novel.
yeah. Results, absolute, gradient norm. Yeah, these results are just showing that yeah, showing that MHC is more stable than the HC by having lower loss and gradient norm. Yeah, they show that MHC the fluctuation of the gradient is similar to the baseline and it's much smaller than the HC one. Training ability baseline. Yeah, this show there's some improvements with Um, 5 points, 3 points. Yeah, that seems some good. Well, these are not so good. Yeah, there are some good improvements on these the first two, but the others are not so big. Scaling experiments. Well, I don't quite understand why these the x axis are all flops because they claim that the scaling property. The first is compute scaling curve. They compare the model size from 3B, 9B, and 27B, but the x-axis are still flops. Then the token, they compare the token. I think they fixed they used the fixed 3B model during training and they probably use different training tokens. But generally, I think they're saying, yeah, it's consistently better than the baseline when they use different size of models and different number of tokens. Propagation stability. Well, this is about the investigating the stability of this MHC. So they calculate the forward signal gain, the backward signal gain. I think the signal gain just means the the norm of the it's called, I think it's just the norm of the HRES um, matrix or something close to that. It's just
Yeah, I
how
think they did like row sums or column sums or something like that. So it's not exactly the L2 norm, but yeah.
yeah okay. Yeah, but they what they are showing is that the signal gain is close to one, meaning it's it's quite stable in terms of those what do you call it, the signal gains something.
Why? Any intuition as to why? So on the if I'm understanding this correctly, they're on the left, they're looking at like each layer individually, and all the gains are around one, both
Right.
forward and backwards.
If they
Uh,
ran the synchron algorithm infinitely many times, it would be exactly one instead of close to one.
and both of them would be that way. I'm wondering why there's kind of a bias on the backward gain being higher. Um,
Yeah,
why
I'm
is
not
on
sure,
the right
but
hand
on the
side?
right, it's when you accumulate after many layers. So
Right. So why is it that the forward gain they were able to get exactly one? I mean, that's really close. But the backward,
Yeah,
it's almost like the row gains some to one, but the columns don't, or something.
that's interesting. Maybe they remember that the algorithm they just iterate through two steps. Maybe they just end up on one step that happens to be row sum to be exactly
oh,
one or column sum
right.
exactly to be one.
Oh,
When you're alternating
interesting.
row and column, whichever one you end on is actually going to be exactly one. It's the other one that won't be exactly one.
Interesting. And did you say, Ted, these could be done in any order?
You have to alternate for the algorithm to work. But if you had an oracle that told you what the 50 iteration column sums would be and the next 50 iterations of row sums would be, you don't have to actually apply them in that order. You could just apply them all at once.
Hmm.
Well,
I
but I
wonder if you
think,
could center that bias if you kind of alternated which one you end on.
yeah, I think that's
Yeah,
possible if
actually,
you start
yeah.
with,
That'd be cool. Yeah. Even rows
yeah,
end on row sum and odd ones end on
Right.
column sum. Yeah.
yeah. So maybe you can decrease
Right.
this curve.
Right. So they both would be 1.3 instead of one of them being 1.0 and the other being
Right.
1.6.
Hmm.
Assuming
Yeah.
they're equally important, I don't know. I would, if anything, I would think the gradient one is more important, but I don't know.
Yeah. 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 Maybe. Um, okay. Visualization of learnable. Um, yeah, I think HC, they still compared HC and MHC. So this is just the H-res, that's the mixed matrix. So they show HC, they have large numbers sometimes, these 1.8 something, 6 something. But in MHC, they are more stable. Yeah, I have to be quick. We already time
If you
stability.
want to, Chair, if you want to pick a point, we can, we've got one more paper left to do, right? Pick a point that's
Um,
a good stopping point, and we can finish up next week if you're good for that.
The last
um,
paper is
the
very
last paper, yeah, it's very simple.
Okay.
So I think the only important part is this one. So it's a modification of the how you calculate the H-res matrix. Instead of using that sync what? Sorry, I don't remember the name. Yeah, synchron knob algorithm. They use this PK is permutation matrix, which just means you have permutation vector and then you permutate them in the matrix. Like each row is has only one number one, other all zero, and each column is the same. So if you mix a lot of them together, um, weighted sum together, then you get the doubly stochastic matrix. Not sure if I stated clearly, but the idea is you don't have to like do those iterations, but you can just sum up certain matrix to get the same property. Um,
Yeah. So it turns out we didn't really talk about it, but one of the mathematical properties is that the set of stochastic matrices um, is a closed set under multiplication. So if you multiply a doubly stochastic matrix by another doubly stochastic matrix, you get another doubly stochastic matrix. And in addition to that, all doubly all permutation matrices are doubly stochastic. You can kind of see because in every row and every column you have a single one and all zeros. So they're sort of the obvious doubly stochastic matrices. But then it turns out that every doubly stochastic matrix is just a convex sum of other doubly stochastic of the permutation matrices. And
yeah.
geometrically, it's too hard to because a 3 by 3 um, doubly stochastic matrix has 9 numbers, so it's a 9-dimensional space, and there's 6 permutation matrices for 3 by 3 matrices, and so it's too hard. But Claude told me that these 6 permutation matrices live in a 4-dimensional subspace of the 9-dimensional space. And if you were to connect them all together, if they were vertices and you were to connect them to all together, then basically doubly stochastic matrices are the convex hull um, of this volume that connects these 6 vertices together. But so if you have 2 permutation matrices, like the identity matrix and the one that just swaps columns 2 and 3, um, then if you just take half of each, then you'll still wind up with a doubly stochastic matrix. Um, and so what they do when they parameterize this is instead of saying get a random matrix and then convert it to doubly stochastic, just actually parameterize it as 6 alphas um, multiplied by the 6 known permutation matrices, and you will have a um, a guaranteed exactly, well, floating point rounding, exactly doubly stochastic matrix when you sum those 6 together.
So
Yeah,
n
yeah.
is n was the number of independent residual streams. Is that right?
Right. Yes.
Yeah.
Gotcha.
And so there's always n factorial permutation matrices. So
Gotcha.
for n equals 3, it's 6, and for n equals 4, there's 24 permutation matrices.
Got it. So you
So they
just
said,
reparameterize it, and then by definition, you're going to be doubly
yeah.
stochastic.
So instead of running sync or NOP, you do these 24 things and you add them together, and Bob's your uncle. You have a doubly stochastic matrix.
Cool. That sounds a lot easier.
Yeah, the only problem is the sync or NOP scales a little bit better. Um, whereas this n factorial grows very quickly.
But was the four versus was the four independent streams, was that the actual number they were using in the models, or is that just an example?
Yes, no, they actually trained and released a MHC model with 4.
So these matrices aren't that big then.
No. You can totally do it with 4 because there's only 24
Yeah, yeah,
permutation matrices. But you can see it doesn't, like, even 8 like is
yeah.
starting to make me think, hmm.
Right, right.
Well,
Yeah, it grows quickly. I get that.
yeah, yeah.
You
Yeah,
could do
they
sync or NOP on 8 by 8 matrices.
yeah. Yeah, synchronoptic grows slower than the factorial.
Yeah.
Yeah, I think synchronop is something O of n squared divided by some epsilon. Is yeah, it's something like n squared. Well, this is much,
Yeah.
the factorial is much higher.
Yeah. A factorial is exponential. N squared is not good, but quadratic is still way better than exponential.
Yeah, yeah. Yeah. So yeah, with this approach, you get exact the doubly stochastic. So they say it's even more stable than MHC.
So
And
now that
also,
so now those graphs we were looking at before, both forward and backward, should both be exactly one. Is that right? With that
yes,
numerical
yeah,
precision.
yeah. I don't remember if we have that figure. Yeah, I think
Yeah.
this shows the that value. So the one it's always one with this the factorial stuff,
Yeah,
and
yeah, yeah.
the MHC they fluctuate around one. It's not exactly one.
Very cool.
And yeah, another advantage they say that you don't need to write those customized kernel because it's just a simple sum of matrices.
Right.
Um, yeah.
That makes sense.
Yeah, I think that's all the
Yeah.
stuff from the papers.
Thanks, Terry.
Okay. Yeah. Thank you. Thank you very much.
Yeah, that was
Yes.
very good, Jerry. Thank you. And Ted, thank you for your insights as well.
Yeah, yeah, Ted, thanks.
Nice.
So thank you very much.
Oh,
Um,
you're very
Uh,
welcome. Yeah. So for me, the TLDR is if you ran out of data and you ran out of parameters compute for model size, you could do this MHC thing, and at a cost of a 7% increase in computing, you would get a better model. So if you're OpenAI and you know you have whatever 5.3 and you need 5.4, this is a plausible, pretty easy win in order to get your next little bump for, GPT 5.4.
Yeah. Yeah, and uh yes, someone saying that the next version of DeepSeek is going to use MHC, and another I think called Ingram, which is an improvement on the memory of the model. They move the memory out from the dense layer into a hashing like memory, or it's a lookup table like memory. So yeah, it's the rumor saying that DeepSeek next model will be based on these two techniques.
Yeah, so yeah, they actually released that paper already. So
Oh,
it
really?
it has lookup tables for bigrams and trigrams, and it's a vast oversimplification, but basically, um, the the bigram trigram lookup table says like if you're saying something like the United States of America, um, that it can predict, once you say the United or the United States, it can predict that the next few tokens are going to be of America. Um, and that saves you from having to spend the first few layers of attention and feed forward just to do that very simple prediction. And so in the Ngram paper, it showed that they were able to get better results um, even when they reduce the size of their mixture of experts in order to compensate for the GPU memory required for these bigram and trigram tables. So they shrunk some of the parameters of the model in order to fit these tables into memory. Um, and it still built a better model than without it because the bigrams and trigrams are fairly easy to calculate and
Yeah.
it ended up relieving. But because it's DeepSeek, they didn't just do a vanilla thing. They actually took MHC and they added that
Yeah, yeah, yeah,
bigram
yeah,
trigram stuff to it.
yeah, yeah. I'm seeing in that paper. Yeah, they can also offload the memory into off from GPU onto the machine's memory because that Ingram it doesn't depend on any internal state. It just depends on the input input token embeddings.
Yeah, they talked about that, but I don't think they actually built that. They just said theoretically there's a way you can try to
Oh,
do that.
oh, okay. Yeah, okay. I didn't notice that part.
Yeah. Um, so at least DeepSeek seems fully bought in on this hyperconnection stuff.
Ted, your observation about the HRES, you're saying that an orthogonal HRES would be better than a doubly stochastic. Did I
I
understand that
I
correctly?
don't know if the mixing it does would be better. Okay.
Okay.
But it would be L2 norm preserving. So even this third paper that Terry covered, which has exact doubly stochastic matrices, the eigenvalues are guaranteed not to be bigger than one, but they can be less than one. An orthogonal matrix, it guarantees that the eigenvalues are all exactly one or negative one.
Right. I wonder if you could do a reparameterization as they did in a way that guarantees orthogonal HRES. Is there anything like
Uh,
that?
I don't know. There is some kind of parameterization you can do, but it's not, I don't think it's as simple as just like for this,
No.
they just said sum together some permutation
Yeah,
matrices.
yeah, yeah,
At the end
yeah.
of the day, basically, you can just have rotation amounts.
Right.
And so if you just start with the identity matrix, and I don't know exactly the math, I think if it's an n by n identity matrix, if you have n minus one rotation vectors, then you can rotate it into any
Yeah.
thing, right? And so basically, it's just each of those mod 2 pi gives you a
Yeah,
rotation, and that will give you an orthogonal matrix. I don't know if that's a useful way of parameterizing it. And I don't know if it's cheap. I guess it's not super expensive just to do the cosines and sines in order to do all the
right,
rotations.
right.
But to your point, it is
Yes, that is.
definitely possible to parameterize just by saying, take the identity matrix and rotate it.
Yeah.
In the
And you might need to also flip a coin whether or not you
Which
throw in
way
a
you rotate?
reflection,
Yeah.
yeah
a
in
I'd have to
one
look
a
at that.
reflection.
in the muon optimizer, the technique that they get the orthogonal matrix, is that something can be used, or does that preserve the doubly stochastic? Uh,
Yes. So the muon technique is using approximating orthogonal matrices. However, that only works when your input values are all between 1 and -1. And
oh,
so uh, the residual stream in a transformer is not bounded. It
well,
is allowed to
well,
grow.
I think we are talking about that just that HRES matrix, which is
Yeah.
a pretty small matrix, and I think the value is just 0 to 1.
Oh, yes.
Hmm.
So if you use something like tan H, like they do in the original HC paper, so the values are between 0 and -1, then you can approximate an orthogonal matrix by using what the heck was the muon algorithm called? Uh,
The some Newton some
Newton-Schultz
Newton Newton
iterations.
shell.
Yeah. So you can do a handful of Newton-Schultz iterations, and you will have an approximately orthogonal matrix. So that would be another way to do it, is use the same trick that Riemann uses.
Hmm.
Actually, that it might be
Should
slightly
we?
different math,
I'm
but
wondering if we had a, so it's, I just noticed it's 8:20 to
yeah,
8:22.
we're
Yeah,
So
over.
maybe
yeah, we're over
we
time.
should, yeah, wrap up this one. But Terry, thank you very much. That was really
Yeah,
good presentation,
yeah.
really helped.
You're welcome. Thank you all. Thank you, Ted.
Yeah. Thank you, Terry. Yeah,
All right.
these are a good pick, Terry. These are I think very interesting papers.
Yeah,
Very much so.
thank
Yeah.
you.
So I'm going to stop recording now. Okay. All right. So that's that. We have, do we have anything more in the queue? I don't think we have anything queued up for next week, right? Okay.
Not yet. No.
Um, there was one that I was thinking about. Um, I, it's been a while since I looked at it, as in a couple of months, but um, the DeepSeek v3.2, if I remember, had a different, almost two-layer attention mechanism.
That would be a great one. Yeah, the new DeepSeek attention.
And also I saw something that Google just released, an attention model. Um, so I thought that one, I don't know if we want to split it out into a couple different things, but I could do one. I haven't done a paper in a while, so I could do one on the DeepSeek attention and the Google attention and just try to make it an attention focused discussion, if that's of interest.
Yeah,
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 that sounds
that would
interesting to
be
me.
interesting.
I
Yeah.
think that would be great if you are able to prep that for next week.
Okay. Are you looking up the recent Google?
Yes. So the DeepSeek one's easy. I just wanted to get the name for it. DeepSeek sparse attention, they called it DSA.
I don't remember where I put it. I think I just saw the Google paper today, I think it was.
But they've been, advertising this whole Titans thing, but that's like I think a separate. Oh no. No, what Claude is telling
Sequential
me is the
attention.
Titans thing.
They're calling it sequential attention. I haven't read anything more than just there's the oops, did I get that to everybody? Yeah. Um, I haven't read anything more than that, but it says subset selection algorithm. Sounded interesting.
I saw a paper today on X.com, the
Oh.
Everything app from Zyphra, who I believe are the same. No, that was Writer. I thought they were the same people that did the thing that inspired the multi-decode. But despite them not being those people, I think this looks interesting in that we have online vector quantized attention, or OVQ attention, which is, I don't know, it's just a random little thing. I put it in agenda here. Let me paste it here too.
So Roger, this sequential attention looks interesting, but I don't think it's in a model. It's just a paper.
Oh, okay.
Not
Well,
saying
let
we
me do
shouldn't talk
this.
about it. Just
I'll start with the DeepSeek one.
mhm.
Uh, they're kind of two-stage attention. And then if I have extra time, we'll roll into this. So I won't set the scope too big. And then um, Warren, that paper that you just posted,
Yeah.
online vector quantized.
Yeah, sequence mixing layer that aims to find a better compromise between memory compute cost and long context processing. Sparse memory update that allows it to increase the size of its memory state and consequently memory capacity. That sounds interesting. Theoretical basis for OVQ attention based on Gaussian mixture regression, which sounds kind of spicy to me.
All right, well, let's just do the 3.2, the DeepSeek
Yeah,
paper
you start
for
there
next
and see
week.
where it
And
goes.
then
I'm gonna-
we got a couple other ones that can maybe
yeah,
roll in after that, if that makes sense.
nice.
Okay.
Cool. Oh, by the way, Roger, before you close the Zoom, I responded to your inquiry there about beads. The long and short
Oh,
of
how
it is,
did,
yeah, if you run BD init to start the thing, it should walk you through a little tutorial that allows you to install some pre-commit hooks, and then it'll automatically like remind itself every time it tries to commit. So that might be the thing you're looking for.
okay.
And then the other useful one is BD Prime. If you just if you are in a Claude Code session or whatever, and you hop into the terminal with exclamation mark, and you just run BD Prime, so it ends up in context, then that'll give it that'll set it up. But yeah, Beats has some stuff that will periodically remind it every time you clear the context to do it.
Okay. Then you've done that in open code. Does the agent in Cloud Code also will work with that?
Yeah, they're just they're Git hooks, they're pre-commit hooks.
Gotcha.
So, and then I
Okay.
think there's also a couple of hooks for Claude on compaction and slash clear it'll trigger that as well.
Okay. I found a video if people are interested. I can post it to agenda and we can decide if we want to discuss it. That was talked about Claude extensions, all the different Claude extensions. Warren, for you, this is going to be like the back of your hand, but it was nice for me to
There's a lot there,
understand.
so yeah, it's good. It's good.
Yeah, I'm remembering when you first you presented months ago, but you had said, you need to keep reading the release notes on Claude because there's so
It's
much
every
coming
week,
out.
yeah. I
Yeah, and
got plenty
this,
of material for my meetup every single week when I just go
yeah,
over all the
exactly.
blog
This
servers.
really captured it.
That's wild.
Yeah.
So,
All right. By the
all
way,
right, sounds
Roger,
good.
we're way over time, but I just wanted to say so. I got some LLM help. That question we had at the very beginning about if you have very deep LLMs.
Oh, yeah.
Okay, right. So the fundamental phenomenon is we do know that the residual stream magnitude grows as you get deeper. Okay,
Yeah.
empirically we know that. Whether or not it has to or not, there's some theory there, but for sure we know that it does. Okay, when you do pre-norm, it it normalizes the inputs to the layer, so the layer actually doesn't know what the magnitude of the residual stream is.
Okay. Yeah.
So there is nothing fundamentally restricting a layer from saying, oh, I'm a late layer, so I'm just going to shout really loud and output things of magnitude 5.
Okay.
But it has no way of knowing if the residual stream is magnitude 1, 5, 50, 1,000.
Yeah. Yeah.
So
Yeah.
it can't adaptively do that right.
Well, it should learn the weights are going to be learned at the layer.
That's right.
So
So
it should know.
it could
Oh,
just
good.
know that statistically by layer 37, it's probably around magnitude 8. So I'm just going to shout 8s. And by the
Right.
time you get to layer 49, I'm going to shout 20s. But
It's
um,
harder
it's hard because it doesn't really have any feedback signal. And then weight decay is actually fighting it.
fighting against
So
that.
if
Yeah.
you don't have a direct gradient signal telling you go louder, then weight decay is just going to keep
Brings it
shrinking the
down.
weights. And
Okay.
so that's why de facto all the layers are like outputting norm one, sort of, or
Gotcha.
whatever.
Did you notice how fast those decay in that little two-dimensional plot? How fast those were decaying off?
Which
Wait,
two-dimensional plot?
remember in one of the ones that Terry showed, there was a two-dimensional, and it showed like the influence of one layer on another.
Oh,
I mean, I guess I don't know what the scale was, but the color dropped off very rapidly. I was kind of surprised how rapidly it dropped off. So, but yeah,
Well, for the post norm graph
uh,
or for the HC
I
I
HC
think
graph.
both the HC and the post norm had very rapid drop off,
Yeah,
mostly.
yeah. That's correct. Yeah,
yeah,
mostly, yeah.
yeah,
Yeah. Um, but it's not to say they're not reading the residual stream. This is just the multiplicative effect of the H-res.
right. All right. Well, thank you, Ted. Yeah. I was wondering if it might. I remember you describing it as getting very loud, the residual stream getting very loud. And I was wondering
Yeah,
if it
I
might
knew
be.
that, but I was like, but then why don't the layers just start shouting louder? And then Claude reminded me the layer doesn't know how loud it is because it gets pre-normed, and so it doesn't
Right.
really know.
Right.
So
Interesting.
yeah.
Okay,
All right.
okay.
Thanks, guys.
8:33. So we'll wrap it up. Thanks, everyone.
Thank you.
All right.
Yeah.
See
Thank
you
you,
Thank
guys
Ted,
next
you.
Terry.
week.
Great job. Bye.